Alright, so today we start with code. So if, I don't know if you have it, but yeah, there is like a notebook that you can download. It was already there last week. It's called something like bagging, boosting to fill. So if you want to like to follow along, like I wanted to do a bit more of I code, you code. In reality, there's not too much to fill just because like otherwise, you know, like we can't really go at that pace. But I thought it's nice to see like an actual application, and so you have it if you want it. Yes. Okay. Hello, video people. Say something, please.
Hello.
Hi. Hi. Okay. So yeah. So if you want, we will start. Like I just want to have I have a couple of slides presenting just like the science problem that we are looking at, and then we'll dive into the notebook that was posted on GitHub actually last week and this week. And if you need the link, I mean, I think I sent an email to the Google group that has the link to the GitHub. So we've been talking about classification, so I thought, okay, I'll show you classification problems that actually we've dealt with a lot. Well, the way we're doing it today is on simulations, and now that the data are coming in, I'm sure you're not surprised to hear that they're very different. But anyway, at least it's real, and so I figured, you know, like there's like a paper you can read, and so this is a survey, like an ongoing survey. It's called HETEX. Sorry, I should probably put this mic. So. Good? Yeah? Okay. So I should also calm down a little. And so the survey is called Hobby-Eberly Telescope Dark Energy Experiment. It's a spectroscopic survey, and the goal is to find galaxies that are far away enough to be able to detect or non-detect dark energy at redshift around 2. So the redshift of the survey, like, you know, the galaxies in which the survey is interested in, is between 1.9 and 3.5. So we're looking at look-back times of, you know, like several, like, you know, around the 10 billion years ago range. And the main issue that the survey has is that because the way you're measuring the distance there is looking at how these galaxies are clustered on the sky in 3D. And so it's really important that your measurements, or, you know, like your selection functions, only includes these very far away galaxies, and it's not contaminated by things that are closer, because that really messes up your angular clustering measurements really poorly. And so for them, the idea is it's quite important that you can select only the faraway galaxies. However, in our example, we're going to do the opposite. So, you know, like there's going to be like 2 types of galaxies that we look for, which for HETEX are the typical contaminants. But we're going to look, and this is like the reason for that is just that the faraway galaxies are actually much more common. And so I wanted instead to use an example in which you're looking for something that is not as easy to find, because this is actually, you know, something that happens more often in science. And so we are going to look, you know, at 2 types of galaxies, and we are going to search for the ones that for HETEX are contaminants, but actually, you know, they are on their own interesting galaxies, just a smaller redshift. So the 2 classes that we have are the faraway galaxies are so-called Lyman alpha emitters. The Lyman alpha line at 1216 angstrom is one of the most powerful lines that we have in the universe. And it has it's an ultraviolet when observing rest frame in galaxies that are far away. But for galaxies that are very far, the spectrum gets stretched by the redshift of the universe, and so actually can be seen at much larger wavelengths. And for HETEX in particular, because we're looking at galaxies at redshift between 2 and 3.5 approximately, this means that, you know, the regime of detection is between 3500 and 5500 angstrom, which is like the range of, you know, the observed wavelengths of the telescope. Now the contaminants are this other type of galaxies. They're called O2 emitters. And O2 means oxygen 2, and the line that you'll be detecting there has like a natural, like rest frame wavelength, when observed in the lab, of 3727 angstrom. And so it's easily redshifted for galaxies at much lower redshift, between like 0.3, 0.5 to the 3500 to 5500 range of detection of the survey. This makes sense? So far, I know there's also like not astro people, so I'm trying to go a little bit slow on this. And so this is an example. Say that we're detecting this line. And you see here you have like two spectra of galaxies. And actually, these are simulated galaxies, and I'll tell you more. It's the same spectrum, top and bottom, just redshifted by a different amount. So this one here is the LAE, the Lyman alpha emitter. Right? So this galaxies is observed at a redshift of 3. And this is where the really strong Lyman alpha emission line comes in. And this one here, this blue one, is an oxygen 2 emitter galaxy observed at a redshift of 0.3. And you see that the O2 line is observed in exactly the same location. Now, if you had the whole picture, it doesn't seem so difficult to distinguish between these two galaxies, because they're closer, they're less stretched, they're more luminous on average. The LAEs, they're farther away, the spectrum is more stretched, and on average they are less luminous. The reason why they're less luminous, actually I should say less bright, this is kind of wrong, is because they are much farther away. They are at a much higher redshift, and the apparent brightness of an object scales with its inverse luminosity distance squared, which means that in general, these galaxies have a much lower apparent brightness level. However, the information that we have does not include the whole picture. Otherwise, there wouldn't be like much of an issue in distinguishing. So, first of all, like the detection range of the survey only includes a small window. And so you have of course, the remainder of the spectrum has a lot of other information. For example, here you see like a bunch of other emission lines that are not observed in the case of an LAE. And this could be really helpful, but you don't have, in many cases, like those lines are not observable within the range. And then you also have, so what we measure is the strength of this line. And in some cases, we can also measure the so-called continuum of the galaxy, which is like on average how bright the galaxy is on the two sides of the line. But our threshold for detecting the continuum, which is also another helpful information, because you can see like that the continuum level of O2s is typically much higher than the continuum level of an LAE, our threshold is actually pretty high. And so in many cases, you have a non-detection of the continuum, which, it's more likely to make the galaxy an LAE, because LAE typically are non-detectable, but not all the time. And then you can build an additional feature from the emission line flux and the continuum, which is the equivalent width. Now, for astronomers, you know that this is not exactly right, but the equivalent width is basically something that says if I measure all the flux in the continuum and I stretch it over a rectangle whose height is the average brightness of the continuum, what's the width of that rectangle? And that's why this thing is called equivalent width. This is not exactly right, but you can think of basically of the ratio of the emission line flux divided by the continuum. It's not rigorous, but in terms of roughly what that is, this is what it boils up to. And finally, another thing that we know is the location in wavelength at which the line is detected. And this might not seem very important, because in the end, according to the redshift of the galaxy that are observed, that is not bound by anything, the line will travel right and left. But actually, there is at least a small part here. This is like 3,500 angstrom, and the natural, the rest frame wavelength of the O2 line is at 3727, which means that anything observed to the left of that is an LAE for sure. And so actually the location of where the line is observed is also important. So we're going to look at this problem, and we have basically 4 features. And we're going to take a look at, like how to do it with a machine learning algorithm like the ones that we have seen last week, the random forest and the gradient boosted trees. Sounds good? Questions? Comments? Shall we take a look? And keep in mind that these are simulations. And so in simulations, everything works really well because it's true, like you put in the properties of a galaxy that you're observing. And in particular in these simulations are not even like spurious sources, so it's really like neat. And so when we'll see like, really nice numbers, yes, it's encouraging, but just keep in mind that data always look different. So for this, let me see which one I want to use. So I'm going to use this notebook, which was called Bagging Boosting Methods to Fill. And if you guys want to play along, you can open it and type with me. Can you see it in the back? Is this like large enough font? Yeah. Okay. So the first thing is just takes a minute, but this is just like the imports of the stuff that we need. And if you don't have a laptop and you want to look, I'm sure your neighbor may not mind if you want to you can look here or you can look there. I mean, it's up to you. Okay. These are just some warnings that I'm, in general, they say, you should never suppress the warnings, but I found that at least these categories is not a big deal. And then I'm also reporting here, this is like a helper function that allows you to plot the confusion matrix. Last time I think we printed it out. It's kind of nice to see it in plot because the graphical version has more information. Okay, and so here I have this file that I made, and I'm using pandas. It's a CSV file, where CSV stands for comma separated values. And so I'm reading it in with this command, pd.read CSV, and then the name of the file, it's separated by a tab, and I'm indicated that if you see any line that starts with the hashtag, which actually has another, is it called the pound sign, then this means it's a comment. Okay, what else do I want to do? Well, I want to take a look. So this creates an object that is called a data frame. And data frames are really nice for data manipulation. So one thing I can do is if I do data.head, it will show me by default the first 5 rows. And so you can see here that the first 5 rows, the first one is like a type. This is like an LAE O2 label. And then I have like the wavelength where the emission line is detected in angstrom. The flux in the emission line, which as you can see is tiny. The continuum flux density in units I can't remember, and the observed equivalent width of the line that is like built as that ratio. All right, so what do I want to do next? Well, I want to check the size of the data sets. That's in general, it's nice to have. So I can do data dot. I could do shape. That tells me that there are like 5,436 objects in this data set. I can also do count, I think. Go away. And so this actually counts column by column, which is not particularly helpful in this case because I have the same number everywhere, but this is something that helps you see if there are missing data. Like if your columns have a lot of missing values, doing a count by column will tell you whether you have that thing to worry about. Okay, another thing that I kind of wanted to do is that, because a nice thing of pandas data frames is that you can actually access the column by calling their name, as opposed to having to remember where they are. It's I wanted to rename them to something that is a bit easier to read. And so I could do, actually, I'm lazy, so I'm going to copy and paste it from here. It's not cheating if you did the work before. So here we go. So I'm going to say, okay, like I'm going to rename my columns to something that has only, like one word and no spaces, which makes it a little bit easier. So I'm typing data.columns equal, and then you give the column names in square brackets, which means you're providing a list, essentially. And I put them here in single quotes. So if I do that, and then I look at my data frame again, you can see that I have like basically the same things, and they have just been renamed to something which is a little easier to type. And let's see, what else did I say I wanted to do? Rename columns. Okay, so far so good. And I think we actually possibly use these names, so I would say if you're following along, you may want to give the same name for these. Okay, now first thing you should do, we could build a model right away. But I think it's kind of nice also to just like, take a look at what the data look like and see if we see like any red flags or, obvious outliers or other things that we want to be aware of. And so one thing that is kind of nice to have is this data.describe. It's a property of data frame. And so this basically gives you column by column, well, how many values you have, and what's like the mean and standard deviations, and then like various like percentiles, like minimum, maximum, various percentiles, which I guess is interesting. But for us, because we have two different types of objects, and we're really interested in understanding what are the similarities and differences, so we can discriminate, it's kind of nicer to do this by type. And so data frames have this cool property called group by. And so we can first group by type. And if you just do the grouping, it looks like this. No. I can't, it's just a property, I take it back. So if I do group by type, and then I hit describe, then I get the same thing, but now the two rows are the LAEs and O2s. And this gives me the aggregated properties of this type of object. So it's kind of like nice when you have like different classes and you just want to build a little bit of an understanding of what's different among the classes. And so the first things that we see is the count. And so as I was mentioning, there are like about 4 times more LAEs than O2s. And that's why I kind of want to focus on this class, unlike what heptax would be doing. And that's just because, like I pick a special like redshift slice, like as you go across cosmic time, these things change, but in this case, this is what we have. And then you have all of these other things. So basically you get the statistics column by column. Now you can see here that is in the middle, like the standard thing, like the default behavior is that you don't see everything. And so you can actually hit the next line to say, hey, I want to see all my columns. And I can execute the same command that I had, data, group by type, and then describe. And so you will have everything. And then because frankly, having like all the percentiles is not the most helpful thing, one thing that you can do to just like reduce the amount of output is to say, I don't want these percentiles, bye-bye. And so now you can say, okay, the wavelength, they're sort of like observed a similar average wavelength, which is not surprising, but we can start looking at the differences in the other variables that we have. So this is emission line flux, and so you can see that, like there is a significant, not quite an order of magnitude, but a significant difference in the emission line flux. This is the continuum, and you can see that in the mean of the continuum, you also see a significant difference. And this is the equivalent width. And once again, you see that the LAEs, as we expected, have a much larger equivalent width than O2 on average. All right, So what I'm doing here is like, okay, let me look at the equivalent width just to say, like 1, and I'm going to plot the histograms of both of them. Surely, let me take this range off first. So I thought, okay, let me plot them in a histogram, the equivalent widths for both objects. But you see that if I don't specify anything, what I'm getting is a histogram with 20 bins. And this is going, kind of surprisingly, between 0 and 160,000. And the distribution, like G2s, seems to be absent from the distributions. And like there is only one significant bin here. So what does this mean? How do you think that this pandas is choosing the range to divide the histogram in 20 bins? Any guesses? Well, I'm going to say probably is looking for minimum and maximum. And we can actually go back up to check what was the maximum of the equivalent width in the two cases. And so you can see here that the maximum of the distribution of equivalent width for LAs was, in fact, around 160,000, which probably is not a physical value. Right? And so this is like the kind of analysis that would tell you about, like there are really wacky objects that you probably need to take care of before you start learning, because otherwise they will skew your entire distribution. So that's why here, something that is nice to do is to specify a range. And my range here is 0, 500, which is also what you had if you're following the notebook. And so if you do that, now you see something that makes a lot more sense. It still shows you that on average, O2 emitters have much lower equivalent widths. Like the vast majority falls within this first bin. And the width of each one of these is 25, since it's like between 0 and 500. And then you can see what's the distribution of LA's equivalent widths. But what we have learned from here is that there are some objects with really extreme equivalent widths that typically, especially when you're doing machine learning, you kind of want to eliminate because your algorithm wants to learn what is the typical behavior. And so it will be like, it can be like, just like any other model, it can be severely thrown off by these strange things. So what I did here is, it's a little bit, here I wanted to be fancy and do it in one line. But so what I'm doing is like, I want to eliminate outliers. I'm defining outliers as objects for which basically their value in each one of the columns is more than 3 standard deviations away from the mean. Okay, and so this sort of like, makes sense. And I'm gonna do this on all the data other than type. Type, you see, is not a property. In fact, it's the target. It will make sense actually to take it away from my data frame. But at this moment, since it's still there, I'm saying, okay, drop the type column. This is what this means. And then I'm going to say, consider all the objects for which the value is less than 3 standard deviations away from the mean. So this is what this line is doing. And I'm going to build a new data frame called cell data for like select data. And so you can see that there were only 6 objects that I eliminated this way. Sort of like if half of my data set goes away, that's somewhat of a worry. But if it's only like 6 objects out of 5,000, then it's probably a good idea because I'm only throwing away a tiny part of the data. And so I can hope that I'm not significantly affecting my distributions. But at the same time, I make sure that really strange objects don't become part of my learning process, since probably their properties are so strange that there is not much to learn from them anyway. Okay, and so now I can do the same things as before on my select data frame. And if we look at the equivalent width, you can see that the mean for LAEs has gone down a little bit. The median, I would expect that has changed less. And the maximum is still like a really high value, but it's at least it's like less crazy than what it was before. And so I feel like at this stage, I can be happy with my selections and move on. But for your own problem, you may decide that you need to be like more selective or less selective in the cutoff that you make. Yeah.
I think it's like 100 points.
So again, it's 100 objects. Yes, you're right. Sorry, 100 objects. I think I flipped those digits in my mind. And so so we have about 100, and so what's that? 100 out of 5,000. Is it 2%?
Yeah.
Okay. Okay. So correction. You can decide whether 2% of the object get thrown away is something that is too restrictive or less restrictive. You may decide that 3 sigma standard deviations away, you may make it like 4 or 5 to make sure that you only take out very strange objects, or you can leave it as is if you believe that this is like the right thing to do. Okay, so now I'm almost ready to make a model. And to do that, the main thing that I need to do is I need to turn this into a NumPy array. And this is because all the scikit-learn algorithms take as inputs numerical features. And it's not a problem for anything. What's like the one thing that doesn't work at the moment? That is not, what's like the one type of information that I need to give that is not in numerical form? Type, right? It's a string. And so this is something that at the moment I cannot yet do. And so there are several ways to do this, which Stack Overflow will tell you all about. The simplest is using this utility from scikit-learn preprocessing. So this is a package that will have like a whole bunch of sort of like helper functions to transform your data. And so the simplest that you have is this label encoder. So I can define an object, which is like a label encoder object. And then I can create a new column, which takes the type column from my cell data frame. And I can use this like fit transform. So the fit transform is sort of like a combination, as you can guess, of fit and transform. So the fit part sort of like takes a look at what values you have in the original. The transform part takes that thing, whatever it is, typically a string, and turns it into numbers. And I think the standard behavior is to turn them into integers. So here, do this, and then I take a look. You can see that it was like LAE, 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 and then like the ones are hopefully for O2 emitters. So it has detected 2 types of variables, and it has turned them into zeros and ones. And so right now, I can now, this basically assigns a value of 0, calls the negative class, the first type of object that it encounters. For us, we say that we are interested in the O2s. So arbitrarily, we are assigning the O2s as the positive class. So we don't need to do anything else. But had it been the opposite, say that we were interested in LAEs and we wanted to call those the positive class, then we would have to flip. The other thing that I think is good to remember here is that this is, I think, sometimes also called one-hot encoding. It's a typical method that you have to transform categorical variables into numbers. For 2 classes, it works quite well. For multiple classes, it's trickier because say that you have, I don't know, 5 classes, and say that these 5 classes are not related to one another, right? Or you don't believe that, like there's basically contiguity in classes means anything from a physical perspective. If these classes are encoded as 0, 1, 2, 3, and 4, your algorithm will think that the classes that have been associated to 0 and 1 have more in common than the classes that are associated to 0 and 4. which may or may not be the case. So transforming the categorical variables into numbers, also introducing a concept of distance, which perhaps was in your data. Like, for example, with Justin, we're now looking at this application of galaxy morphology. And so if you think about, like you want to look at like the different types of galaxies, if you put them in a sort of order going, I don't know, like from elliptical to spiral, and you encode the different classes as being, sort of like turning into one another, then this is fine. But if you have, like 4 categories that have nothing in common, then probably this is not the way to proceed. And in this case, it's better to have one new column, one new variable for every new class that you have, and give those a 0, 1. But say that you're tracking, I don't know, people who are coming to a building on Monday, Tuesday, Wednesday, and Thursday. And maybe you don't have any reason to believe that the people who come like Monday and Tuesday have something in common or more in common than the people who come Monday and Thursday. Then you make 4 new columns, rather than turning these, comes Monday, comes Tuesday, comes Wednesday, comes Thursday into 0, 1, 2, 3, you make 4 new columns, which will have like a 0, 1 flip. And so that's the way of doing the encoding when you don't want to introduce a distance in your data that is not necessary. But for us, with 2 classes, 0, 1, there's no problem. So we can keep going, and we can assign a new column to our data frame, which actually it's not a new column, I'm replacing the type column. I always get these, and I feel like I've done so many things to make it go away. So I'll just do it. And now if you look, you see that the type has been turned into a number, and so now you can use the column to give to scikit-learn. And so I have to define an x and y, so this will be like features and target. They need to be in 2 separate arrays. And so I'm going to call them x and y. And so x and y are my cell data array, where I'm dropping the type columns, because they should go in the labels array. And then cell data.type becomes my target variable. Yes? And then I'm doing another thing. And this is actually for tree-based methods. This is not important. Today we're going to talk about support vector machines, which was uncertain because it's a bit slower, but I like it so much, and it's like a different, like completely different type of algorithm, so I thought I would at least present it. And so for things that do decisions, rescaling your data is not important. But for things that do linear algebra, rescaling your data is quite important. Because remember that you had something that has order like 10 to the negative 16, and something of order unity. And so in general, this kind of range is not particularly well controlled by things that do matrix multiplications. And so in general, for us it doesn't matter, but it's not a terrible idea to so-called standardize your data. You can do it, like scikit, like the pre-processing has sort of like, a scale property, but just to see what it is, I'm just like, sort of building a normalized feature array where I'm basically trying to get to like 0 mean and 1 standard deviation. And so if I describe this array, basically for the means, I'm now finding values that are very close to 0 for all columns. For the standard deviation, I'm finding values around 1. So this is just basically to bring every column to a similar numerical range to avoid numerical instabilities. Yeah? Okay, so we have our algorithm then. Are you all caught up? Okay, so we'll start with the random forest classifier and with standard parameters. And so this means we have hopefully imported it here, yes, random forest classifier. And so nothing particularly new. Let's say we'll say model equal random forest classifier. Yay, we have a model. Now, what should we do? I can't remember what we got to last time, but we have mentioned that it's a good idea to do k-fold cross-validation rather than just building one train and test split, so that 1, we use all data, 2, we get a sense of what's the typical performance rather than like only one realization. And so for this, I have these 2 really neat functions called cross-val score and cross-val predict. So I can say, let's see, cross-val score, and then I think it's model and then they call it normalized x, and then y, then the default value of the cross-validated splits is 4, I believe. Let's do CV equal 5. But, okay, let's do it like this and see what happens. All right, so this is not terrible, as you can see. The scoring parameter here, the standard scoring parameter, is accuracy. So if I want to change it, I could do, for example, this. And this will build the model, and so you can see that accuracy was around 94% probably. If I ask for precision, it's the purity of my data set. In other words, like of all the objects that have been called O2, since O2 is my positive class, how many of those are truly O2? So you can see it's like not that great. And you can also see that there is a bit of a fluctuation here. And we can also look at recall. Our class is not particularly rare, right? It was about like 20% of the total. So it's not a terribly imbalanced data set, but it's kind of like interesting to see. And you can see that here we are just like around the 80% mark. So this is another reminder that, like if you do it without thinking about what metrics you're interested in, you look, okay, 93, 94%, that looks great. But it really, if you're interested in the completeness of your sample, then you are at a lower point. Now, a couple of things just to improve these. First of all, something that we didn't do, but is quite important to do, is to make sure that your data are not in order. Because cross-validation score, if I remember correctly, in standard behavior, doesn't randomize the data first. So one way to avoid this is to use a stratified k-fold here, with shuffle equal true, and then, let's see, n splits equal 5. So here I can put it in this so that you're able to at least see the entire line. So I'm defining a cross-validation object, and I'm saying rather than just making n splits, which just would take the first 20%, second 20%, third, do this with shuffle equal true. This makes sure that the data are randomized, and this is always a good idea unless you're dealing with time ordered data. Like for time series, you can't, you can't predict the past using the future. But in general, it works. And then I'm also using this stratified k-fold property. And stratified means that basically the objects will be, yes, randomly selected, but trying to keep approximately the same distribution of the two types in each of the folds. And so typically, this is what you would want to use. So now this is my cross-validation object. I can do the same. What did I do? I didn't execute this cell. Okay. And maybe I can make this an actual object. And then I would do scores.mean and scores.t. And so this gives me, if I'm using the recall as scoring, I would see, okay, I have a mean of about 81.5%, and this is my idea of the standard deviation. And so this, as I was mentioning, this is where you can get an idea of how much your scores can fluctuate just because of random fluctuation in the data, which means that you're always building your algorithm on the training set and applying to slightly different data. I see some people still typing, and so I want to, and this field one, I will also post it. And so yeah, for precision and recall, this would just
Viviana?
Yes.
I'm getting slightly different numbers than you. Does that mean that I've type something in wrong, or is that something that can happen? Like my mean is 0.8058.
805, definitely, because it's well within the standard deviation. So what I would expect from this is that your random realization, because we didn't set a random seed, and so you will have a slightly different realization of the data. And so yes, and so in some sense, having here, for recall, you're mentioning, Stephanie?
Mm-hmm.
Okay, yeah. So I would expect a standard deviation around 2.5%, and we are at 0.815, and you are apparently at 0.805. So yes, I think we are well within the realm of expected random fluctuations.
Okay, great, thank you.
All good here? Okay. So this is, how we do cross-validation. And then another thing that I promised here is that I want to visualize and plot the confusion matrix. Now, as you can see here, this is just giving me the scores. Explicitly, I haven't built yet the vector that has the predictions. And this is what cross-val predict does, another great little function. And so we can say our y-pred is cross-val predict, and then it has similar arguments, but it doesn't have a scoring parameter. Of course, because it's just predicting. The way the predictions are built does not depend on the scoring parameter, right? So while the scores depend on the scoring parameters, because this dictates what's reported, in the predictions we don't have that. But what this function does is it still does k-fold cross-validation using the cross-validation object that we are providing. And basically, it's recording the predictions for the test set, each one of the, let's say, 5 times. And then it's assembling this vector together. So your vector prediction is actually as long as your original array has all the objects, because every object has been in the train set 4 times and in the test set 1 time. And so for each one of those, we have now, like 5 sort of, smaller prediction values, prediction vectors, and we are assembling them together to make one. So this is the object created by cross-val predict. And I can use it to build my confusion matrix. Confusion, oh, maybe I have to do matrix.confusion matrix. Yes. And the arguments are always the true values first, the prediction after. And now I can use my plot confusion matrix. And I have to go and remind myself of the signature of the function. So forgive me, I'm going to go back up here. So CM and classes and normalize equal false means that it will give you the true numbers, not percentages. And the color map is the blues. So I just want like the simplest one. I can do CM, which is like my confusion matrix objects, and then I have to say classes equal and provide the names so that it knows what to write. First goes the negative class and then the positive class. Yeah! And so this is telling us more explicitly what our classifier is doing. Right? So this is like, the O2 is the positive class, and the LE is the negative class. And so here we have true positives, here we have true negatives, here we have false negatives, and here we have false positives. And this is basic, as we mentioned, if we are dealing with a binary classifier, these numbers are all that we can build about our classifier. And we can decide, okay, we can build like a custom cost function, which gives different weights to these and this type of error. In principle, they all count the same. And finally, we mentioned the receiving operating curves and the area under the curve. And for this, we mentioned that we'll need to build the true positive rate and the false positive rates, but basically looking at different thresholds of classification probability. In other words, this, when the classifier builds its algorithm, it would say, underneath or, like behind the scene, it can build like a probability. And then it would say, okay, if the probability of this object being an LAE is more than 0.5, I'm going to call it an LAE. And this is how this probability becomes a class. But if you're willing to take a look at what happens for a bunch of different probability thresholds, then you will build the ROC curve. And so to do that, we can use the predict probability or predict proba property of the classifier. And this is how you can take the same classifying algorithm but say, hey, rather than just predict a label, give me the probability. It will build like a length to objects with the probability that the object's in the first class, the probability that the object is in the second class. Now, one slight trick is that in order to call these, I need to explicitly call the fit property of the algorithm. And this means that I cannot use my cross-validation score, cross-validation predict shortcuts that I had above. I have to build a train and test set explicitly. Because on those one, I can use fit to fit my train data, and then I can do predict probability on the test data. So this means that we are sort of like taking a step back from our k-fold cross-validation, but this is just for the purpose of looking at these curves. And so this is what we have for our classifier. This is, I hope, I didn't put my bad. I should put labels on this. So label, and then that's R, and Y label, and then TPR. Okay, so this is like the false positive rate. And this is the true positive rate. And a perfect classifier has a box like this. Right? And in general, if you see like a line like this, it means that your classifier has no power whatsoever at distinguishing between classes. And like the more you tend to this, like perfect box things, it means that as soon as you put like any threshold, your false positive rate stays at 0, and your true positive rate stays at 1. And normally it's just like a trade-off. And the area under the curve is actually 0.96, which is quite good. All right, one last thing that we mentioned last time about all these ensemble methods, especially the tree-based, is that you can use them to do feature ranking. Which means, if I want to know which features are more important in order to build my classification algorithm, I can look at all the splits that use a certain feature, and I can calculate the average decrease of impurity given by a particular feature. And so important features that carry more information will be more often part of splits that lead to a large decrease of impurity. And features that are basically useless will almost never be found in significant splits. Now, as I mentioned, this one sometimes, if there are features that overlap in, that are significantly correlated, sometimes this splits the information across features. So this is actually more important, or quite reliable in figuring out what's useless, and less reliable in doing a top ranking. But nonetheless, we can take a look at what it is here and see what happened. So in this case, which feature, what do we have? We had equivalent width, we have emission line flags, we had continuum, and we have wavelength. What ranking do we expect? With the caveats. So this is the case in which the caveats really apply, because there's lots, basically 2 out of 3 of these are not independent. Only 2 out of 3 of these are independent. But what would you expect? If I had to pick one thing, if I tell you, okay, I'm only giving you one of these, which one would be more important? in distinguishing LAEs and O2s.
So you're only getting one?
No, I'm just saying, I'm just asking you to guess the ranking. And so if I have to ask you, okay, which one is the most important, I guess it's the same question as if you were only to have one, which one would you pick?
Equivalent with.
Equivalent with. Other ideas? Let's see. Yeah, I guess that this is not done by type. So let's see. So to do my feature ranking, I can go here. And so basically after I fit the model, and this is not doing any train test split, I'm fitting everything, because this is just meant to like build understanding. And then I can look at feature importances. And I mean, it's not, this is saying that, okay, I have like about 9%, 20.25, 0.28, 0.37 for the ones. And it's kind of nicer if I can actually plot it and give a label so that I know what I'm talking about. And so this is the feature ranking now that includes name. And so look, in this realization, equivalent width was actually the highest. So that's nice. And then you have continuum and emission line flux that have been given the same importance. And wavelength is actually, this is like, a decent amount of information. But it's less than the other, which is somewhat expected because, like there is a region in parameter space where wavelength is informative. But like to the right of that 3800 angstrom and beyond, basically the wavelength doesn't tell you much about the probability that you have. And so this is the feature importances. But for large data sets, when you have like hundreds of them, and you want to reduce your data space or just like sort of like explore, then this can be quite helpful in getting rid of like many that will have like tiny importances. Does it make sense? All right, let's see. So now, how can we improve? Let's say that even if our class is not terribly rare, we are at a recall of like 80%, maybe we don't like it. We are at a precision of 80%, maybe we don't like it. So, and just to remind ourselves, the model that we're using is a random forest classifier. Bootstrap equal true. Remember that we say one of the ways the random forest randomizes is creating different bootstrap samples, so you can verify that this is true. And these are the other parameters that you have. And so there are parameters that are associated to the tree, similar to what we saw in the decision tree. For example, the minimum number of instances in a leaf node, which is min samples leaf. The minimum number of instances requiring a split node, which is min sample split, and this go really hand in hand. The maximum depth of the tree, which at the moment is none. The criterion that is chosen to decide whether a space is worth it, which for us is gene impurity. Then we have the randomization parameters, which are whether bootstrap is true or false, and the number of features that are used in building tree. For us, n is only 4. So we know that one way to make more random trees, and so like diminish variances and increase the expense of the bias, is to choose less than 4. Now in a small data set, this may or may not work out. And we also have forest parameters, and so for example, the number of estimators or tree in the forest can be adjusted. The standard value is where is estimators? Oh, it's 10, and it will be increased to 20 in the next generation. But in general, you want to, like at some point it will plateau. So adding more trees in general, it's always an advantage because we've seen that it makes the variance become lower, but for a large number, you also expect it to plateau, and so you don't want to go too high. And so I thought maybe you guys can play with your favorite parameters to see if you can beat this performance. And if you want to do it only with one, I would say let's use recall as our scoring method. And let's see, our benchmark was, what did we say? 0.815, like 81.5%. And so I would say, if you want, you can sort of play around with these parameters to see how much you can beat it. If you need help, I'm happy to help. Anybody got more than 81.5%? No? Yeah, do you want 2 more minutes to try? Should I show you? Try the other parameters. You all email what's going on. Any ideas on what to try? Mm-hmm. Yeah. Did it work?
Yeah.
Okay, very good. So you put max step to what?
2.
2 and increase. Okay, so this will reduce overfitting. It's pretty drastic, having only like 2 allowed splits, but still very good. Any other attempts? What's something that should always work in improving the scores?
The class weight.
Well, the class weight in this case in an imbalanced data set, and because we're looking at the less common class weight would also always probably help if we're looking at recall as our metric, right? In the sense that increasing the weight even to misclassification in the O2 class would bring us, we lower the precision, we'll sort of like pick up more objects, but always increase them. So that works. But in this case, there's also a number of estimators. And remember, for a random forest, you can never go wrong with increasing that number. You may find that actually there's not much difference between 10, 20, and 50, but in general, if you're like, okay, I have like, one shot, what do I do? And you have like a low number of trees, you know that increasing the number of trees can only help. Because it will not change the bias of a single tree if you're not changing your randomization technique, but it will reduce the variance if you have any. So that's one. But I'm going to give you my solution, which of course is. So what I'm doing here, and what I would recommend doing, and we'll see a bit more later, is the way to do this is sort of like creating the grid of parameters you want to try out, and hopefully trying them all at the same time. Right? So to play with, we usually like play with one, and this maybe can limit the ones that you want to try. But what I'm doing here is that I'm creating a dictionary of parameters. And so I'm saying, okay, for max depth, I'm using 3, 5, and 8. So it's not far to what I'm saying. For max number of features, I'm only picking 2 and 4. It's a small data set, so I can say I can experiment with that. For number of estimators, I'm going to 10, 20, and 50. And for class weight, as Rob was mentioning, I'm trying 1 to 1, 1 to 3, and 1 to 5. You could also do this as balanced, and this would just take sort of like the inverse of the frequencies of the 2 classes, but this is like another way to do this. And then like here, this is just like calculating how many I have because I want to see the time scaling. And then I can use this function called grid search cross-validation. And in this way, I use a random forest classifier to which I'm feeding this dictionary of parameters. And so this is, like a way, which is, of course, like a bit more time consuming. And so this is like the tricky part. But this way, you get to try a bunch of parameters together. Now, luckily, we're dealing with random forests, which are pretty fast. If this was SVMs, we wouldn't be able to do it online. But, and you will have this, I think, like for me, I have 270 fits in total because I have 54 model candidates, and for each one of them, I'm calculating 5 folds. And I think this takes about 20 seconds. And so you can see here that I'm given a set of best parameters, which gives me like a recall score of 97%. The class weight that was chosen is 1 to 5, which is understandable because I'm asking for recall. Maximum depth of 3, so this also means that that significantly cutting down the trees or pruning, as they say, is better. Max feature is equal to, actually this is, like I just ran it 20 seconds ago when I was like not on screen, and this was 4. And number of estimator was 20, and previously was 50. So keep in mind that, that the fact that this is the best doesn't mean that there are like, several models that performs comparatively well. And actually in the next example, we'll see how to take a look at the overall results of the grid search so that you can actually see, like the different combination of the And the only other things that I think is worth showing is that if I do the same thing, but I choose accuracy, for example, I would expect that I will get fairly different parameters. Which is, like another reminder that the model that works best is really not one, but it really depends on what kind of metrics to use. And so here, my maximum accuracy score is 95%. It's achieved with a class weight of 1 to 1, similar max depth, and then I guess I think a lower number of estimators. probably because this is a problem that doesn't have as much variance as the previous one. Yay? And so this is how, in general, you can start doing parameter optimization. Now, the trick here that we will explore afterwards is the fact that these scores are still, they have been obtained on the test code with the optimized parameters. They're still not a fair measurement of the generalization error. Because when you use these parameters that you have optimized on like new data, your new data don't know anything of how the parameter optimization procedure went. But these scores do. Because I've chosen the parameters that gave me the best test scores. And so we'll need to do like, one more layer of complication in order to properly evaluate generalization error. But this is the way you would optimize your parameters. And actually for gradient boosting models, it's quite similar. So we can sort of look at gradient boosting classifier and do the same thing that we did here just to benchmark. Accuracy by just scoring equal. You can see that actually sort of just like at base level, I do a little bit better. But whether or not the difference is statistically significant is to be seen. I'm getting about 84% plus or minus 0.5%. And for random forest, I had 81.5 plus or minus 2.5. So, it's a little bit better perhaps, but I wouldn't be overly excited. And so here I thought, okay, we can do the same, but just for the sake of moving on, which I'm sure we want, I'm just going to do the same thing to see which one. This model, you can see that we have slightly different default parameters. One that we mentioned last time is the learning rate. This gives you a sense of how much each sequential classifier is participating to the overall learning. And a low learning rate means that typically you need to add more sequential trees or stumps to get to a good result, and a large learning rate means that you converge more quickly, but at the same time, sometimes you get stuck. And so, for performance of the test, you have a standard number of like 100 estimators. These are like little stumps that are built sequentially, not parallel. And so, here is like a new grid of parameters. I'm changing things that are similar. Actually, let me make these numbers a little bit bigger. And let's read this one. Recall. And so we can check the performance, but also the timings. And I think what we were saying last week is that they have a reputation to be quite fast. But you can see that at least here, compared to the random forest, I'm not seeing these. So I don't know. Yeah, time per mode is actually 0.17 seconds. And I think up here, time per mode will be about a third of that. I I don't know though if this is just because of the really small data set. It's possible that the advantages are seen on larger data. So we're at here, okay, and so this is like we are around 85, well I guess it's like 85% for the call, but it is a little bit unfair because I'm not playing with the class rate. Is it even one of the parameters? And so this tells you that, just because I'm dealing with an imbalanced data set, if I want to recall as my scoring metrics, if I'm shooting for completeness, then probably like a random forest is better, just because I have the freedom to tune that handle. I'm curious to see what happens if I'm using accuracy here. You guys have the patience with like 30 more seconds. And so here we were like around 95%. And so we end up with a similar score. So subtleties that we'll see some, if we have time today. I feel like, I'm always like running around behind myself, but is one thing is like, if you do a grid search, there is an object that is created called figure results. And so you can actually, like use it to build understanding of which parameters are more important to play with. And if you're like sort of like, you see that you are optimizing at the edge of your parameter search, that may tell us that it's worth like expanding your grid in that direction. Another thing is that, yeah, to evaluate the generalization error, we need to do nested cross-validation. Because these scores that we have now are still not a fair representation of what will help on new data. Because these are test scores that reflect the fact that we are working with optimum parameters. And they know about that because they have been, those parameters have been chosen to maximize those test scores. Now, in our work, by the way, we ended up, and this is, I feel like, quite common in science application, defining our own metric. Right? So far, we have talked about, accuracy, precision, and recall, which I like to call like purity and completeness. But for example, in this paper, where we're actually, this is what these data, these simulations were generated for. What we're, because we are looking at, yes, LAEs versus O2, but our final goal is not to pick galaxies. Our final goal is to compute the angular diameter distances of this galaxy. So what we did instead is we built a whole bunch of simulations, like simulated galaxies using like the properties that we have. And from there, we actually fit a multi-polynomial function of this is contamination, which is 1 minus purity, and incompleteness, which is 1 minus recall, to the error in the angular diameter distance. And basically, we chose this polynomial form, and we fit all of these coefficients. So this is how we derived our cost function. And so I feel like, in the end, yeah, from a binary classifier, there's only a few numbers. But in the end, what matters for you will depend on the application that you have. And so if you want to do that in code, you can. And I put an example here with like a simpler loss function for that. But there is a function called make scorer. And so you can just like define a loss function. This is just like a random thing that says, okay, look at the log of 1 plus the absolute value of the difference between prediction and real value. And then in cross-val score, you can implement a custom scorer. The only thing that you need to do is to say whether greater is better is false or true. In other words, if you're dealing with an error, or if you're dealing with a score. And so I feel like this is also maybe nice to know, in order to be able to tailor your scoring and your optimizations to the problem that you have. And I left there even some like other things that could be fun to try if you guys feel inspired. And at the bottom here, this is a function that I made for myself. It's called check train test that I just thought I would share. It basically creates 5 randomization of the data, 5 random train test splits, and look at the difference between the scores. course, to diagnose high variance, since I end up having to do this a lot, I just put this function here. All right, so I would say this is all for this part. I want to talk about support vector machine next. Shall we take a few minutes break? Okay, so I'll see you back in a few minutes. And online people, everything okay? I'm going to take it as yes. And so in practice, information, so this one is the only one that says, because these three things, basically only two are independent, and because of this, they split information randomly between the three. That's why I was saying you can trust the useless ones, but the ranking you cannot trust unless your features are
I have a question about the scoring that you set up for the whole.
Yeah.
Is it useful to know, I guess the assuming the error distribution is linear, and that the factor is like primary distribution is like on the power. Like I think that is usual form, but like how I don't know how
and
how does it equal like
so it's just a series.
Yeah.
scoring?
I don't know, because actually when we were looking, for example, we didn't find much. And so we experimented with a bunch of
The only reason.
and so in the end, we figured, okay, we have found something, we thought that something encouraging was like that.
So,
As we went higher, like the polynomial space, the efficiency kind of
it's important that like you don't get biased.
and
by
more
this.
unstable. So we figured, okay,
I was thinking about
truncated here, and I have to remember my second order.
Do you think that like
There is
that
a
more
place
biased yesterday?
where, it's an approximation, so you can test.
So how do you optimize your like ABC cases? Like there's a
I've seen a
power
lot of
power exponent part, but
Like,
also just
everyone, like,
constant.
did people or
right?
people
Like,
more like
Right.
you optimize constant first and then like optimize constant.
No, we use like this function, like multi-polynomial fit. And so we realized like a whole bunch of simulations for which repetition matrix we knew what that was. And then we used like a small fit, type for example, that basically fits all of the same time. I mean, in practice, I do believe what you say, but no, actually, take it back. I think you need like the same as when you take a line of these slightly different result if you take the intercept pairs and slope. You want to like, and so I think also here we had 6 parameters. I think it just split 6 parameters and have to find the goals.
That sounds like very expensive.
It is, well, I guess it depends on the.
I'm gonna black this out.
So if you have like a very large data set, yes, you may want to go sequential, or just maybe this comes with a bit of a problem of accuracy. But then for us, it was like small enough that we were right, because we had like an analytical function that we could use like on the simulations, we have like real error, and so.
So your errors
Still for us.
errors like such as the I don't remember exactly like ABCD,
Mhm.
those things are coming from your survey information.
Well, so the values are like the two values that we had, basically we have a Fisher matrix function. So we can make any realization of the simulation.
I see,
D
no
is
grade,
a guess.
like a simulation.
Exactly, yes, because that's yes.
That makes sense.
Yes, and so yeah, having that luxury, then we could do this.
Uh-huh.
If not, I think you would need to go with like sort of like intuition, for your like have a form, like a function form that is also. Like for other things, yeah, like I've done the same thing, like experimental with my classic.
Do you have any like different documentation for those Fisher matrix or properties? Is it just like a likelihood like secondary prediction? Or
Yeah, I had a paper, like if you search for Galfish, I did this like as a Fisher matrix error calculations for like galaxy survey. They may have the formalism, and if not that, I think my focus side should work. And if not, it's like, it's still not, send me an email.
yeah, I mean I will have
Yeah, Gaussian shades. All right, beware, I'm going to start again. So the next thing that I thought I would talk about is an algorithm that's very different from what we have seen so far. So one of the main issues of tree-based algorithms that, as we have learned, the only decisions that we can make are parallel to the features. And so we can build boxes, and we can build like small boxes, and we can build large boxes. And we haven't actually experimented with feature engineering, which is, think about this and, like how you can provide features that are more relevant and so easier for a tree-based classifier to pick. But I thought that it would be nice to see at least one example or very different algorithm. And also because I've been studying the mathematics of this because I felt like I didn't understand for a long time, so now I'm very excited, and so that's why you guys are getting it. So, please forgive me. And so this algorithm is support vector machines, and it's a really nice parametric algorithm. And so, and then I want to show you how to do the nested cross-validation to, sort of like complete the procedure of fitting for parameters. So support vector machines are or were actually before all this deep learning craze, one of the most popular machine learning algorithms, and they're actually quite flexible and accurate. The main con is they're slow, as my students know really well because this was not like a popular assignment. So the idea here is that I have two classes of objects as usually, and I want to decide how I can split them. And because this is an easy case, as you can see, it's possible to find a line, and actually the goal of at 0 level linear support vector machine, the goal that you have is to find a line. If you have more than 2 dimensions, the line will be a hyperplane. They can separate the classes. Or in this case, you can see that the solution is not unique, right? You have a whole bunch of linear separations, and all of these are achieving the goal of separating the 2 classes exactly in this really simple problem. So which one should we pick? That one, yes, very good. So if we had to decide, how am I going to split the 2 classes? How am I going to find this optimal separator? What would be good properties to have? Ideas? That one?
I guess you have the answer.
Oh, no, it always happens to me. I don't know. I thought I had taken all of these diagrams back. Why? All right. Well, as we were saying, so if the data are separable, we can find the decision boundary, which is the line that maximizes the separation between the 2 classes. We want to make as a clean cut as possible. And so this means that basically if you look at, 2 examples, like one on one side and one on the other, and these, by the way, these are called the support vectors, and we'll see why in a second if this doesn't continue advancing. Pause, take this. Then basically what we are saying is okay, find our bound. I feel like someone is, I literally, I paused the presentation, it was paused. I think anyway. So we're looking for the separation that maximizes the distance between the boundary and the closest examples on each side, which are called the support vector, and this is called margin. So we're looking for, an optimization problem where we are finding a separation and optimizing the width of the margin. which is the distance between support vector of opposite classes. The reason why these are called support vectors is that really, like, they support the margin, and basically they are the only training examples that affect the classification. For once you know what these, like in this case there are 3, it could be 2, it could be 4. Once you know what those objects are, then you will be able to classify new objects just based on the location of these ones. And this is like a desirable property. Now, as you can imagine, in many cases, you have problems that are not exactly separable, but you still get a sense. For example, here, it's still like fair to say that most of the red objects are on this side and most of the blue objects are on this side. If you were to try and catch this example here, you would probably end, first you cannot do it with a line, and remember we're trying to do this with a line. Second, you probably end up with a lot of overfitting because it just looks like that's a strange object as opposed to something that we want to learn the properties of blue objects for. And so the next step is to say, okay, I still want to maximize the margin of the separation between the two classes, but now I can add these slack variables, and this means that I can allow for misclassifications, and misclassifications will pay a price, like a penalty, but basically I can obtain a new problem where rather than just maximizing the width of the margin, I am, let me call it, minimizing 1 over the width of the margin, which is the same thing as maximizing the width of the margin, while at the same time minimizing the penalties paid by these objects that end up on the other side. So misclassifications that typically happen near the boundary. Okay, so this becomes like a constraint problem where I'm now maximizing the sum of these two terms. So I'm still shooting for like the largest possible margin, but if this comes with like a huge penalty here, then in this case I will, like there's a trade-off in between them. And so this is all that linear support vector machines do. Now, this deals with, some examples. For example, things where either there is a linear separation between the two types, or there is a linear separation with some mistakes. But as we know, in many cases, we have data sets that are not linearly separable, like this one. For example, this. This is like a 1D data set, very modest. Is there like a simple rule to separate the objects? Right? If you had like to draw the separation, what would you draw?
On the second 2 lines.
Right, not with a line. If you can draw any shape, what would you draw?
Circle.
A circle, right? I could do like, or an oval even. I could say, hey, like I want to have a line here and a line here, like my good old decision tree allowed me to do. Like I could only make lines, but at least I could make 2. And in this case, you're telling me I'm only allowed 1. Fair enough. So, like an alternative to being able to draw a circle is to actually remap your data themselves into a higher dimensional space. And so in this case, I'm going from 1D to 2D. And while, it's not the easiest to see here, this means that now my data have become separable. With this, it's a small margin, granted, but still, like I now have, achieved this property of separability. So the whole idea of support vector machines is that I can first take my data and look for a line or hyperplane that can separate them. If not, I can remap the data to a higher dimensional space where, because the distances are larger, I have better chances to be able to separate the classes. And so this is sometimes called the kernel trick. So the kernel is, well, it's not exactly, you can think about, for example, here, it's another like 2D case in which I would like to be able to draw a circle, but I'm only given lines and hyperplanes. So what can I do? I can actually take these, drag it off the board, make it like a 3D space, and then I can use the hyperplane to cut over. And so the function that goes, it's a function that takes me from like my x original coordinates in 2 dimensions to like a new mapping file of x that is in this case in 3 dimensions is closely related to the kernel. So in particular, the mapping function defines a kernel that given a training example and a new example defines this mapping, which happens in the new space. And so typical kernel functions that are chosen can be linear, can be polynomial, or can be Gaussian. So this is an example of data not being separately in the input space. It's unfortunately like an example taken from medicine, so those are always like a little bit gory. But here, if you use like a Gaussian kernel, this is the new distribution of your data. You're basically given like a height to the points, and now you're able to visualize off your hyperplane here. Now, what's the magic thing about this kernel trick? So the magic is that for well-defined kernel function, it turns out that you don't need to specify the mapping function because, and this is like, the beauty of the mathematics that I got lost in the last few days, it's possible to rewrite the decision function, basically the function that tells you, give me the coordinate and I will tell you whether the objects belong to one class or the other class, not as a function, explicit function of this phi that tells me how I'm going to the higher dimensional space, but of the kernel themselves. And the kernels can be written as the inner product of the support vectors and your new example. And on top of that, despite the fact that you're moving from an n-dimensional space to a much higher, sometimes infinite dimensional space, the complexity of this operation is O n, which keeps like the complexity of the algorithm contained. So this is a tiny preview of the math, of like the way I understanding. So let's say that you have the equation of the boundary, which is that equation where like the vector w is like perpendicular to the boundary. Then basically you can rescale it so that you have like the 2 lines of the margin to have equation wx plus b equal -1, wx plus b equal 1. This is just a data rescaling. This means that basically the decision function tells you that you have exactly this on your, like if a point is on the boundary, and then you will have less than -1 or more than +1 if an object falls in the like one or the other category. And so for all correctly classified examples, your decision function will give you either a number larger than 1 or a number which is less than -1. Now at this point, you can maximize the width of the margin, and with the constraint that for all correctly classified point training examples, it will be true that the product of y, which is either 1 or -1, times this equation, which is the equation of the boundary if equal to 0, is positive. Because for negative example, this is less than -1 and this is -1. For positive example, this is +1 and this is larger than 1. And this is like quadratic programming problem. So it's solvable with apparently with like, commercial algorithms. So you could stop here. However, there's like a nice trick to solve this efficiently, which is, it turns out you can turn this constraint maximization problem into a Lagrange multiplier formulation, which means that basically you're able to write a Lagrangian as a substitution of this problem and to minimize or maximize that Lagrangian. And this also means that you can write the decision function, which is this, as exclusively a function of an inner product of each one of your training examples, or actually of like the object you're considering with the training examples. Just becomes like a scalar product. So far, so good. Now, in the non-separable case, you add the slack variables, and so you have just like a slightly different, but still solvable with Lagrange multiplier optimization problem. And then to solve, you define this mapping from x to phi of x to this higher dimensional space. And then the kernel trick, which is also known as Mercer's theorem, is that if k is a semi-positive definite matrix, then the inner product of phi of x times, sorry, phi of xi times phi of xj, which is basically like the inner product in the new space that you should calculate to be able to get your decision, is only proportional to the kernel, which means basically you are never operating in this space. And this is kind of magic, you know, like I've seen it done for like sort of like polynomial, you know, it's like when you go from, you know, say like x1, x2 to like all the polynomial features. And you can literally like build all the features, which is like your phi of x space. And then you will see that, you know, all the possible inner products between these features become equivalent to what you have here in the polynomial kernel. Like the only terms that you're allowed in the inner products are the terms that are provided by your polynomial kernel. And so basically this means that we have a decision function without ever having to pick that function. And so we can go to arbitrarily high spaces, in fact, even infinite dimensional spaces, while keeping the inner products finite and while keeping this operation of order of n. And this is, I feel like this is the reference that I use. I used many, but this is phenomenal. And so I feel like if you actually are curious to see how this works, you know, like sort of like much better than I'll ever be able to tell, I think these are the notes that you want to look at. Anyway, hopefully this gives you an idea of how this works. Now, what are the parameters of SVMs? So, well, the first one, as you can imagine, is the type of kernel. And so what you have here is some data. Do you want me to turn one light off? Is it better or it's okay? No? How many PhDs?
Only easier just to solve this problem.
Yes, exactly. Oh, look, yeah. Well, this looks great now. Yeah, perfect, thank you. So these are like the same data that you're seeing, like the blue and the red. The only thing that is changing, so it looks like a bit of an optical illusion. The only thing that's changing is the type of kernel or the approximation that you're making. So the first parameters is like, okay, what kernel we're choosing. A linear kernel is really like just another way of saying linear SVMs. We're only allowed to divide with like planes. The polynomial kernel, as you can imagine, basically this means that like the shape of the boundary is now able to take a polynomial form, and you know, like the higher the degree, the more like curvy it can be. Now, if a common choice is a Gaussian kernel, which is called RBF for radial basis function by scikit-learn, right? Gaussian are just like a type of basis that you can express for your space. So if you're working with the Gaussian kernel, which is common, then you have an important parameter called gamma, where gamma is the wiggliness of the boundary. And so a low value of gamma will bring you like close to the linear case and have like a very simple shape for the boundary. A high value of gamma will be able to be wiggly, and as you can imagine, it's also more prone to overfitting. And then you also have C. C is the penalty function for misclassifications. And C, we have seen it already, is that term that is like in front of the sum of the slack variables in our optimization problem. And so basically C is a trade-off with the width of the boundary. Having a large width margin is desirable because it means that I've created a really clear separation between variables. It means that I'm confident. But sometimes having like, you know, a larger margin means that my misclassifications will explode. And so in general, if I assign a large penalty to misclassifications, I will end up with a small margin. If I assign a smaller penalty, I will end up with a large margin, just because of like the trade-off of these two terms whose sum I'm minimizing. And then finally, as you know, this is also something where you have class weight. And so class weight is basically can be expressed as assigning a different penalty according to class. So this is like another way of saying the misclassification of one type, the false positive, for example, are worse than the false negatives. And so you can see here that if you assign equal penalties to mistakes in both classes, you may end up with this boundary. And so in this boundary, let's see, how many misclassifications do I have in this case? How many objects are misclassified by this classifier? 1, 2, and 3, right? If this is the boundary, then I count like, 3 blue objects that are to the left. These are misclassifications. And so accuracy is probably quite high, because I only have 3 misclassifications out of however many data points, let's say 15. However, what would be, if I'm interested in the blue class, what would be the recall of this classifier? It's the number of correctly identified positive examples. So how many of those have I caught? 2 out of 5, which means 40%. So that's not great. And let's see, how about when they're like, okay, the recall, and if it's true positive, value true positive false. How about precision? Precision would be true positive divided by true positive plus false positives. Do I have any false positives? No. So this means that precision is high, accuracy is high, but recall is low. And so if I'm interested in this class, I may want to assign a different penalty here. And so here I end up with all the 5 blue objects being corrected classifiers. So I have a recall of 100%. But I've now introduced a bunch of false positives. And so I'm going down in purity or precision and accuracy overall. So it really depends on what I want to do. Okay, so now we mentioned what these parameters of SVMs are. Makes sense? And so the nice thing compared to our decision trees is that because the SVMs perform this implicit mapping, it means that they do their feature search by themselves. And this is something that we didn't have the luxury of doing in any of the tree-based methods that we saw, where the features that you give are the features on which I can make splits. And that's why I kind of wanted to show you something different. Because, like if you are in a case in which you need to do your own feature engineering and you're not sure where to start, then it's possible that this will perform better if you're willing to take in the hit in computing time, which is significantly higher. So let's say that now I want to optimize my parameters. And we have seen already with this grid search how you can use basically k-fold cross-validation on a bunch of different combination of parameters to find the optimum. But we said this is not fair because there is leakage of information between the parameter optimization process and the test scores. So I cannot trust these test scores. And so the last thing I want to mention is how to do that with a 2-layer process that is called nested cross-validation. So let's say that I have like my overall learning set. And as we know, let's say that we have split it. We'll split it like, in this case, if I do an 80-20 split, I split it 5 times. And then what I want to do is use only this inner set to find the parameters and to train the algorithm. And I want to keep this test set, this 20%, completely outside the parameter optimization process so that the performance that I obtain here truly reflects what I could obtain on new data. And so to do that, I need to go inside the yellow one and do another layer of cross-validation. So here, let's say that this is still like, I'm still like at the outer level, and so I have my outer test fold 20%, my outer training fold 80%. So far so good, now I go inside the yellow. And so I can do parameter evaluation. Imagine that's sort of like, grid search that we did, but I'm gonna do it inside here. So I'm defining another level of k-folding. In this case, I have 4 folds. I try to do like 5 and 4 just to keep them separate so you can have like a visual. Then I can say, okay, on these 4 folds, I will define an inner test fold and an inner training set. And so I can look for my parameters inside here. So let's do it with one parameter, say that we are only changing this, like, penalty of, like, what is it called? Like the soft margin parameter sometimes, or, like the penalty for misclassifications. I have 3 values, 1, 10, and 100. So let's say I say, like, okay, let me try the first value, it's c equal 1. So with c equal 1, I will do, like, in my inner yellow set, I can do this 4 times. Okay, just to get like an average of the performance with the parameter c equal 1. And then I will, like, write down the average of the test fold score on the 4 folds. Okay, now I move on to the next value. Let's say c equal 10. And then again, I can do this process of, like, doing this 4 times, reporting the average performance. And then I do it with c equal 100. So at this point, I've run my algorithm how many times? I have 4 inner folds. How many parameter values? 3. So I have basically, like 12 runs. And so I have, for c equal 1, I had 4 performances. This is, let's say, the average. For c equal 10, I have 4 performance runs. This is the average. For c equal 100, I have 4 performances. Say this is the average. So in this case, which one should I pick? C equal 1. And so its performance is 82%. Right? So this is the number that I remember. Now I can say, okay, this was done on my inner yellow set. And so my winning model, I can apply to the test fold. Right? Test fold doesn't know anything about this process, so it's fair. And I can see how well my model with the optimized parameter c equal 1 that I got from this side does on this test fold. So I'll get the number, let's say that here I also find 82%. Take this number, set it aside. Now what should I do next? Right, so basically now I need to go to the second step of the outer cross validation, where this is my test fold. And so I will redo the process, optimize the parameters here, get a sense of the performance here, write it down. So say that, I get another thing. Maybe I don't even get the same parameters. Maybe for this fold, c equal 10 is a better parameter value. That's fine. All that matters is, like, I'm picking one, and then I apply my winning model to the test fold. I get a different accuracy, for example, 80%. I save it. I had 82% first, and 80%. I continue for this fold, this fold, this fold. Now, the average of these 5 performances gives me the proper generalization error. Basically, each one of these 5 times, I've seen how a model with optimized values perform on test data that the algorithm had never seen before. And probably this will be slightly lower than what happens inside the inner cross-validation, where the test scores they know about what optimal parameters are, but this is okay. And so I will get still a generalization performance, which has a mean, and will have, like, a standard deviation that gives me the idea of the fluctuation. Now, what's going to be your best model? Your best model is still the one that you will find doing parameters optimization, for example, with a grid search on the entire data set. Now, this is fair. This is how you optimize the parameter. This nested thing just gives you the quotable generalization error, because this is the only case in which your performance with optimal parameters is calculating on a test set that has not seen them before. And so I know that this can be like quite confusing what you see so far, but I do have an example in code that basically takes that grid search CV that we have seen so far and puts it inside like another layer of k-fold cross-validation. So hopefully when you see this, it will also be more clear how to implement these bits. So this is an updated summary of how to build a model that includes what we've seen today. So you choose a class of models, and now we have added another one. We can choose the model hyperparameters, but now we actually know how to optimize them. So we don't need to just choose. We arrange the data, we split the learning set into training and test, and use k-fold cross-validation. But actually now we learn how to do nested cross-validation if we want to calculate the proper generalization error. Repeat, repeat, repeat. And then again, of course, if you're not satisfied, you could diagnose bias and variance and see if you can improve from there. And then the final model is built using all the training data, using k-fold cross-validation to find the ideal parameters, and reporting the generalization error that you found here in the nested cross-validation process. So what do you think? I know it's fun, but I thought, hey, you need to see it at least once in life, and then I think, like, hopefully once you have, like, a coded example, this is something that if you want, you can like reuse and readjust. So I don't think we have time to go through today. So here I have, some like additional references. For nested cross-validation, it's actually very hard to find. Like mostly you just find like blog posts, even like the typical data science book don't talk about it, but I feel like it's quite important, especially for us in astronomy, because our main issue is that we never have data sets that are truly the same. And so I feel like the problem of transfer learning, or how well you can expect your algorithm to perform on different data, is quite important. And so I think listing where the tricky bits come from is helpful. So I'm just going to go here for a minute. Where did we go? And so what we will see probably at this point next time is how to use a support vector machine and play with its parameters, and how to do the parameter optimization with nested cross-validation on a very common toy dataset, which is the digits dataset. Have you seen this before? Right, so they're nice, and the one that scikit-learn has is actually not the original. It's nicer because, as you can see, it has images that are much smaller. These are actually 8 by 8, and so this means that basically it's a data set with 64 features, which are like the brightness of each pixel in an 8 by 8 image. The original dataset is quite important historically because it's often used for benchmarking. And so I put it down in this dataset if you want to see them play. In general, when like a new algorithm comes up, its performance on the original MNIST dataset is what's used to say how good it is. But the original dataset has 70,000 objects, 28 by 28, so it's 784 features. And its time scaling is terrible. And so I feel like, for us to play with, this is something that is much more manageable. And so I would say next time we will play with a support vector classifier, look at the parameters that you have here. Actually, this we can probably do. Here, model is SVC, and we can say cross-val score, and then model data, and what do I have? Labels. So see what we get, and you can see that the accuracy is already pretty high, and this is because the data set is simple. And this is like how you would run a simple grid search on a support vector machine. And shouldn't be too bad. We have 260 models then 42 in about 7 seconds. So in 30 seconds, we should have our answer. And this is not yet nested cross-validation, so this will come like the inner loop. Like, this is like what happens inside the yellow set, and we will add the outer layer. But you can see here that with optimizing parameters, I can get to a pretty decent accuracy score. Is it accuracy that I'm using here? I think so, because this is like a balanced data set. And so I can get a 98.5% accuracy just by doing some simple parameter optimization. And these are the results of this is what you get out of CV results. And so you can see that you get, like a summary of the parameters, the test and the train scores for all the splits, and also the mean fit time. And then if I want to see, let's see, scores DF, I created a data frame. And so I just want to see maybe the parameters. And then, let's see, the mean test score, the mean train score, and perhaps mean fit time. Did I do? This needs to be a list, like a nested list. So this is what I was mentioning. It's kind of nice to look at the result of a grid search cross-validation. And so you can basically see, like for each combination of parameters, what are the test scores, which is what we really care about, what are the train scores, and also what like the timings for the fit are. If you want to be a bit more fancy, I could actually do this sort and then by equal mean test score, maybe not score, is it rank? No, sort values, not just sort. And so this will rank them, ascending equal false. And so, if you're looking, to see like the best, and then, to build some understanding of what the other models are doing, this is ranking them by mean test score, which is nice, and this is like the mean train score. And so you can see that for these models, we are looking at, like the winning kernel is often the polynomial kernel for this case. And I think like the interesting bit is to go down to models who are performing poorly. And you can see here that these, for example, are suffering from like terrible overfitting because you have very low test scores but perfect training score. And you can see that this happens when the model is more complicated, as we expect. So either we are looking at RBF kernel with a large value of gamma. So this means like a very weakly boundary that doesn't generalize well, and the large values here, which doesn't help. Or sometimes we're looking at, look at this poor thing. This is not even overfitting. This is just not doing well. Or if we are here, we are looking maybe at a polynomial kernel of a higher degree, which also tend to overfit by creating a boundary that is too wiggly. So I think, this is a good point to stop. We can even like go through this couple of bits next time. And so we will finish by showing how to implement nested cross-validation. So you have at least, like a full implementation of what we have seen today. Sounds good? And then we talk about regression, which it's not too difficult. It's not too different when you're talking code, but of course, like the metrics that you need to use are different. So I want to at least cover a couple of those. And we'll see each other Tuesday if you're around. And if you have your badge is already lets you in on Tuesday and Thursday, so you shouldn't need to do anything else. All right, thank you guys.